This video shows a worked solution to a problem concerning the moment of a force about the x-axis in the context of a practice exam. Question 1, Part B, asks us to determine the moment of the force F about the x-axis. All of the information required to answer the question can be found in the diagram. Here we have a pipe construction which is fixed at B. The origin has been located here, with the x-axis here, the y-axis here, and the z-axis here. The point B lies in the xy plane. The point A is directly above B. The position vector RA describes the location of A relative to the origin. In Part A of Question 1, we used these dimensions to determine that RA equals minus 250I plus 500J plus 400K millimeters. The force F is represented by the vector minus 200I plus 400J plus 50K newtons, which describes the magnitude of the force and the direction of the line of action of the force. Notice that F is applied at A, so the point A lies on the line of action of F. Now that we are aware of the details of the situation that the question refers to, we need to think more generally about what the question is asking us to do, namely determine the moment of a force. The general solution for the moment of a force about a point O can be expressed using the cross product R cross F. R is the position vector of any point on the line of action of F relative to O. Each R lies in the plane containing F and O, and the moment of force about O is perpendicular to that plane. In our solution we will use the point A, since we know it lies on the line of action of F, and we know its position. Now remember that the cross product is not commutative, so R cross F is not the same as F cross R. Using the right-hand rule, imagine curling your fingers from R to F. Then your thumb will point up in the direction of the moment axis. Now imagine turning your hand upside down so that your fingers curl from F to R and your thumb points down. Getting the order wrong will give the opposite direction. Recall that the unit vector I represents the positive x direction. The unit vector j represents the positive y direction, and the unit vector k represents the positive z direction. So we have RA and F expressed as Cartesian vectors, and we can use their x, y, and z components to find M when R cross F is written in determinant form. The first row of the determinant consists of the Cartesian unit vectors representing the x, y, and z axes. The second row consists of the x, y, and z components of R, and the third row consists of the x, y, and z components of F. The question asks us to find the component of M about the x-axis. To do this, we use the fact that the x component of M is found by taking the dot product of I, which represents the positive x direction, with MO. There are two possible approaches, and we will illustrate both of them. Using the first method, we can use the triple scalar product to find the moment of F about the x-axis. In the triple scalar product, we use the unit vector I to represent the positive x-axis, and the moment of F about O is given by RA cross F. The triple scalar product can be expressed in determinant form. We have I with Cartesian coordinates 1, 0, 0. RA has coordinates minus 250, 500, 400, and F has coordinates minus 200, 400, 50. We can calculate this determinant by calculating 1 times the determinant of 500, 400, 400, 50, minus 0 times the determinant of minus 250, 400, minus 200, 50, plus 0 times the determinant of minus 250, 500 minus 200, 400 equals 500 times 50 minus 400 times 400 minus 0 plus 0, which equals 25,000 minus 160,000, and that equals minus 135,000. RA has units, millimetres, and F also has units, newtons. So the moment of F about the x-axis has units Newton millimetres. The standard units are Newton meters, and there are 1,000 millimetres in a metre, so mx equals minus 135 Newton meters. The second approach requires that we first calculate MO. Since we have our vectors in Cartesian form, we can use MO equals the determinant of I, j, k minus 250, 500, 400 minus 200, 400, 50. Then that equals I times the determinant of 500, 400, 400, 50 minus j times the determinant of minus 250, 400, minus 200, 50 plus k times the determinant of minus 250, 500, minus 200, 400. That equals I times 500 times 50 minus 400 times 400 minus j times minus 250 times 50 plus 200 times 400 plus k times minus 250 times 400 plus 200 times 500. And that is equal to I times 25,000 minus 160,000 minus j times minus 12,500 plus 80,000 plus k times minus 100,000 plus 100,000, which is minus 135,000 I minus 67,500 j plus 0 k. And we must remember to write down the units, Newton millimetres. Now, to find the component of m in the x direction, we calculate the dot product of I and MO, which is I dot minus 135,000 I plus I dot minus 67,500 j plus I dot 0 k. That equals minus 135,000 times the dot product of I with itself minus 67,500 times the dot product of I and j plus 0. Now I dot I is 1 since I is a unit vector, and I dot j is 0 since I and j are perpendicular. So the moment of F about the x-axis is minus 135,000 Newton millimetres, which we can again convert to minus 135 Newton metres.